Think forward. Think Research Channel.
Next on Closer to Truth.
When people hear that we discover planets by the gravitational effect that planet has on its host star, they say, you mean you don't actually see the planet? And I say, no. Gravity is as much a signature of something's existence as a direct photograph. If you live in a cabin in the woods, you come to learn what a bare footprint looks like very quickly. And if you see such a footprint outside one morning, you'll start looking for the bear that was once there.
Confidently predict what's going on. What about all the catastrophes, the giant explosions of severe radiation in the universe, comets and asteroids, you know, it's flying all around all the time?
It's bad.
I mean, it's a hostile environment.
But before we wax poetic about how bad it is, consider that the last major extinction, the one that took out the dinosaurs, enabled the tree shrew to evolve to something more ambitious than a rodent or some other small mammal to become what we are today. So these impacts are takers away as well as givers of the diversity of life
some are
on
not.
Earth.
Some are radiation that I think would be destructive.
Some stars die benignly, like our own sun. So another 5 billion
not
years.
Not benign to us.
That's true. It goes to show how much of an astronomer I am. Very the sun will just expand very gently. You know,
Will be a cinder orbiting deep within the sun's surface as it expands through its red giant
but it's about
phase.
5 billion years from now, so we shouldn't be too worried. But the other stars, the more massive stars, and they do die catastrophically, and they can die supernovae, which is very common. At some point, it runs out of fuel, and then it starts collapsing because gravity is the ultimate winner in all this game. So it starts collapsing, and the collapse process itself releases what we call as gravitational binding energy, some of which now comes off in a flash and in gas coming out of at very high speeds. And these supernovae are not uncommon. There's one supernova in our own galaxy every 100 years. So if you're close to one, that could be pretty bad.
So what do you call close?
Certainly 1,000 light years in this definition would be close by anyone's theory of what a supernova would do. And then there are even more exotic, catastrophic things, which is this gamma ray bursts. And gamma ray bursts are they're rare, but their sphere of influence is tremendous.
Is that like the most powerful explosive energy in the universe?
Yes, it's the most powerful directed explosive energy. So they come out as basically beams of light and radiation, and we don't understand all this very well, but we are talking of thousands, many, many thousands of light years as definitely being their sphere of death.
Why is now such an exciting time in the search for life elsewhere in the universe?
There's been something happening on the Earth, which has been the discovery in mid-ocean ridges, in groundwater very deep, of living systems, organisms, microorganisms, that survive in environments we've never believed possible. Incredibly. They chemically process things. They don't need photosynthesis, don't need sunlight to do it. And so I think, for me personally, that is as much a reason to become optimistic, or at least less pessimistic, about finding life on Mars or finding it in another planet or another star than almost everything else.
Well, I would ask, why didn't we know about this? It's just on the bottom of the ocean. Why not 50 yeyears ago?
Just on the bottom of the ocean. These are hard to recover.
Okay.
I think there's two reasons. Going back to my own geological training, it wasn't in the picture. You didn't think about it.
I think, Bruce, what you left out in that whole discussion is the life at the bottom of that ocean does not require sunlight as a direct source of its energy. And once you remove the sun as a requirement, it allows you to think of other ways you might have energy to sustain life. When you teach introductory astronomy, you talk about this habitable zone around a star. And let's take...
Describe what that is.
Yeah, let's take the sun, for example. Life as we know it requires liquid water, all right, in the naive sense of this notion. And so if there's a planet a little too close to the host star, the water would evaporate.
Miles away.
A little too far away, it's frozen. And so there's this sort of Goldilocks interval where you have liquid water. And for quite a long time, that concept dominated our thinking and our discussions about how and where we might look for life around in another star system.
What are some of those conditions?
You need energy. That's the ultimate part you need to get life going. It can be tidal, it can be solar, and so on.
How about extreme cold?
That's interesting because the satellite of Jupiter called Europa has an icy crust. We know that. And probably not terribly thin. There's probably salt water below that. So maybe that's kind of like the Arctic Ocean or the Antarctic. And there are studies that have been done that have detected organisms that really do seem to be able to live in the ice. If you stick a thermometer, it's minus 20 degrees centigrade. It's below freezing, way below. And the organisms not only can survive, but they can apparently live.
But the fluid within them is still liquid,
right?
So they're not in a frozen state.
They're not
somehow.
little solid things.
Solid,
Right.
Yeah.
It's tougher than that because it's hard to find out something's alive. And the usual test is it's got to reproduce. And so unless you can cause it to reproduce and measure metabolism, it's very difficult to say something's alive. So in extreme environments, we're not used to how do you culture those things. It's not that simple. How do you know it wasn't some contaminant from the bucket to pick the stuff off the ground? How do you know what's in your lab? How do you know it didn't come out of the air?
So now, because of these extremophiles, when we think about life elsewhere in the galaxy, we no longer restrict ourselves to this Goldilocks zone because of these how much broader our thinking has become.
Why is now such an exciting time in the search for life elsewhere in the universe?
There are actually two reasons. One is that there's a lot of technology now that for the first time in our entire history, we can address meaningfully the question of planets elsewhere, and perhaps even say something about the existence of large-scale life, by which I mean organisms or trees and so on. But the other one is probably just as important, a bit more subtle, and that's astronomers can now more or less say with a lot of confidence that every time a star is formed, born, then planet formation is a necessary byproduct. So I think this is pretty much the start of a golden era in this field.
Yeah, I'd agree, so especially in the last 10 years, ever since the first discovery, the first announced discovery of a planet around a star other than the sun. And I remember distinctly the day that that planet count exceeded the number of planets around our own sun. So we have people who are now children, for example, who have only known a time where we have in our logbooks more planets outside of our solar system than within.
Ask somebody who's 30 or older how many planets are, and they all say 9. Say, no, I'm sorry, it's about 59 as far as we know right now.
So
80? It's 80.
Wow,
Oh, yeah.
wow.
We'll hit 100 in a minute now.
So how do we know they're there?
Well, there are basically 3 techniques, and in various stages of sophistication at the current time. The simplest one is where the starlight itself is telling you some information. Here's, let's say, a star, and then let's say I'll use a penny as my planet, as the planet's going around. So as the planet goes around, the star is gently tugged, and either you can see
by the
this
gravitational field
attraction
of
the planet, which may be small, but it's nonetheless measurable. So what you would end up seeing is the star undergoes this sort of a motion, and astronomers detect this in 2 different ways. One is something called radial velocity, which is just how the motion with respect to you, let's say, and that's the current technique, which is producing this abundance of planets that Neil.
How big is that radial velocity?
Oh, we are talking of meters per second, tens of meters per second.
And you can detect meters per second differences at
That's part of the
light years.
technologically enabling factors of the past 10 years
and the way to
telescope
and the way to look at this is even a few meters per second is only 1 part in 10 to the 8. That is 1 part in 100 million.
Right.
of
That's
the
a
speed.
big number.
Yeah, that's a big number.
1 part in 100 million
So
you're detecting.
You got to see small variations which are delicate for 1 part in 100 million. And astronomers can do that quite reliably. It took a while, but we are there now.
But I would add that these Jupiter-sized planets that we see around. Okay, can I make a star here with my glass?
A double star.
A double star system. The kind of planet you will discover first is the large planet, and one that is close to the host star, which would then execute one period rather quickly, and you can get that signature in your data.
Right.
And so all of the first waves of data discovered large planets close to the host star. We need a much longer baseline of time, even to find a bigger planet far away.
Because Earth would take a year.
It would take a year. Our Jupiter in our solar system takes 10, 12 years to go around, and so we've only been taking data for 12 years. So we would not have even seen a full orbit of Jupiter by now. I'm often asked when people hear that we discover planets by the gravitational effect that planet has on its host star, they say, you mean you don't actually see the planet? And I say, no, we measure the gravity. And people get worried, well, if you can't see it, how do you know it's there? And I simply say that gravity is as much a signature of something's existence as a direct photograph of it. We have many ways we can measure something is there. Just as you do, if you live in a cabin in the woods, you come to learn what a bare footprint looks like very quickly. And if you see such a footprint outside one morning, you'll start looking for the bear that was once there. You're not going to say, oh, I didn't see the bear, therefore it couldn't have existed. So it's that kind of inferences we make that have been very powerful throughout the history of astronomy. It's how we first even expected there to be the planet Neptune from its gravitational effect on the planet Uranus. No one knew what was causing that. We said the gravity tells us there's an object out there.
The other technique that's been in development for some time now, and it's also coming of age with ground-based facilities at Keck in Hawaii. This is called interferometry. That is,
when you have
when you have more than one telescope and you have to combine the light. And by combining the light, you get more synergism, basically, and the technical word for that is interferometry.
It's as if the telescope was much bigger than either one of those.
Absolutely. With that technique, as well as the next mission that NASA has already funded, called the Space Interferometry Mission, astronomers will be able to go after more distant Jupiters, as well as get, for the first time, around normal stars, we'd be able to look at...
Can I have my glasses?
Yes. And so let's imagine this quarter is a star, and of course this is back my penny. It's a planet. So so here's a star, and you're seeing the star both ways. And as this planet is going around the star and is at some point it comes and occults it. So from that
occulting meaning it crosses its face.
It. Right. Okay. So if there's no planet, if the planet is not eclipsing it, you get all the light from the star. But when it is in front of it, then you get a little less light field.
And some of the planets have been detected with that occulting
Yes,
technique?
one planet has been detected, first identified through this radial velocity technique, and then followed up.
Let's talk about Europa and Mars, because that's close and that's real. And
that's
you
right.
guys...
It's in our backyard. If we have evidence for life ever, whether or not it's there now, but dig down the surface of Mars. Mars, we know, had running water. There are dried riverbeds that meandered, floodplains, river deltas, all this tantalizing evidence that it was once an oasis. And wherever we know an oasis is on Earth, it's got life. So if life ever existed on Mars, that's our backyard, right there.
But
and
there's a problem.
What's the problem?
And that astronomers don't appreciate, nor biologists, I might imagine, when talk about it. The surface of Mars is self-sterilizing. The ultraviolet radiation reaches the surface.
Today, it's self-sterilizing.
It's really self-sterilizing.
Today.
Down for maybe a meter, who knows, 10 meters, we don't know.
Today.
There's no organic material on it.
Today.
Today, you're right. So that means that whatever life did form...
Might have formed.
Right. Did or might. Depending on which side of NASA you're on. Right. But that means that it had to either evolve or be subterranean life, like in the groundwater of the Earth. Because it
So
cannot.
you go digging and you find it, and if you find it, it means that one of our nearest planets has life.
That's glossing over the problem. How far we have to dig. I'm trying to say it's a much more difficult task. It could, in the extreme case, require the equivalent of a human expedition with great big drills.
I'm not worried about how big our shovel is when we get there. If it's got life, it's got life.
Well, okay, so I think that's important. Europa is a different kind of problem, because Europa is not just self-sterilizing. It's in the field of Jupiter's radiation belts. It's lethal for anything that we want to send, including many robots. So you have to build the same kind of technology used in a nuclear weapon, or that you use
Hardened electronics.
hardened electronics and so forth. So again, it's not easy. The extremophile thing we're looking for lives in an area that not just humans can't take, but even robots can't. So it's a challenge. We'll do it. I agree. We've got to do it. And both of those are good targets.
Yeah.
Of course.
Let me come back to my Earth-centered, solar-centered view. I think it's quite relevant, which is the overriding question about us, a philosophical, and it's really a religious question, is, are we something special here in this solar system, and therefore our Earth's kind of special, and therefore the fact that we're sitting here talking is special? Or is that really very common throughout the galaxy? That's probably about as important a question as I know how to formulate scientifically, that could be answered with science. Or are we the freak? Because my hunch, personally, watching this happen, is when you find Jupiter at the distance of Mercury, which is what some of these places have.
Very close in. Yeah.
Right.
If that's the typical thing, and we here are unusual, that's got tremendous implications about the abundance of life, and especially the abundance of human, or at least intelligent life, I think.
Bruce, you may be...
That's my...
I think we're going to take up on you on this.
Are you ready?
Okay, Neil, you go ahead.
No, I'll start first. Okay, go ahead. I'll soften them up for you. No, I'm quite confident that life is not only hardy, given how many environments we find it on Earth, it's also easier than we know to form. First, even if Earth at our distance from the sun is rare, you bring your nearby Jupiter to the sun, and that Jupiter might have 40 moons or 50 moons, some of which would then possibly harbor life. So that doesn't scare me that perhaps Earth at the Goldilocks distance is somehow rare. But there are 2 points that need to be reckoned with. Typically, when people ask how soon did life appear on Earth, they take the age of the Earth and subtract the age of the oldest fossil. And if you do that, you get 4.6 billion minus 3.8 billion, and you get 800 million years. And you say, well, that's pretty quick. But it's better than that, because Earth spent about 600 million years in a period of heavy bombardment, vacuuming up the remains of the solar system. And the Earth's surface was basically sterilized because of the deposited energy and the heat. It was basically molten for 600 million years. It's not fair to start your stopwatch at the beginning of that, because complex molecules can't survive it. Wait till we cool down, then start your stopwatch. 200 million years. That's nothing in a cosmic timescale. It seems to me if life were something hard, it would have taken Earth a little longer than 200 million years, maybe several billion years. And one final point. If you look at the ingredients of life, you learn in your biology class it's water. When you break apart water, you have hydrogen and oxygen. So you have hydrogen, oxygen, carbon, nitrogen. That's what we're made of. The chemistry of these ingredients is the chemistry of life. And you look in the universe, there they are in the universe. Hydrogen, it's also got helium, but that's inert. So oxygen, carbon, in the same order. If we were made of some isotope of plutonium, you could argue that we were rare. So I have high confidence in this. And it's not just dream. I'm not just being dreamy here.
It seems to me planet formation just empirically is very common. And we just know our planetary system well. And we know nothing about the remaining 95%, which is why you need these missions, these other techniques.
How many years do you think it will take to get a sufficient amount of information, as we're doing it now, to be able to make an informed opinion about some generalities about what we can know in the immediate future?
I think it's just money at this point. It's not like we're not smart enough to know what the questions are at this point. By the way, the questions we're asking, just as a caveat here, a lot of the answers we'll be finding may be as a result because we're we're looking for our car keys under the lamppost where the light is illuminating it. There may be systems that, in fact, are unlike Earth that are just perfectly happy making life that we have yet to think of. And science is full of examples like this. But it's just a matter of funding the Kepler mission, the space interferometry mission. So I put it 10, 20 years before we...
I would say the main, the one that will really fill this gap between the radial velocity techniques and the occultation, which have similar sort of biases or similar sort of systems they'll find, is really the space interferometer mission and interferometry in general. So I would say by about 2015, because SIM will get launched in 2009, we'll have a fairly good idea of an inventory of planetary systems.
You're looking for oxygen, in the atmosphere.
So the next step really is how to do more detailed analysis. Occultation, as I said, is a relatively inexpensive here and now technique, but it requires very favorable orientation. So if you find evidence of planets, let's say around Alpha Centauri, then you really want to, you can't expect it to be all nicely lined up for you. We don't know how to make this mission. We don't know whether it should be in the infrared or optical, and this is something that astronomers are more actually thinking right now.
Are they talking about putting telescopes at opposite ends of the solar system? So
telescopes will be...
dream that. We got to work our way.
They will be like, tens of meters to perhaps hundreds of meters, depending on exactly what they end up, which wavelength will operate. And this sort of a mission, which is called Terrestrial Planet Finder, TPF, it's being talked about. It'll be expensive, but again, my own guess is this will happen roughly about 2015.
Let me give you a different point of view. We are in a very early process of discovery and exploration, and it sounds very organized. It sounds like laboratory science. It's not. You look and you find, and the trick is to look properly and broadly. We could find something next year where one of these occultations or another technique shows evidence of carbon dioxide gas, which is strongly apparent in our atmosphere, and also methane gas, which is strongly apparent in Jupiter's atmosphere. What would be significant is those two are incompatible. One is an oxidized gas, carbon dioxide, one is a reduced gas, methane. And they're made of very common stuff. Now, if we got lucky, and if that happens, the overpowering conclusion is there's got to be a disequilibrium going on, namely life, because that's why we have that on the Earth. We have exactly that situation.
Cow flatulence giving us methane in the atmosphere.
And plants giving us carbon dioxide. So we could get, surprised or something comparable to this, or this powerful techniques we've described might not show that. And it's going to be very hard to prove life or even have a high suspicion unless we get lucky with something like that. I'd rather say I think it's likely between now and in 30 years it will happen, sort of a cumulative probability.
That's still within the lifetime of hopefully all of us, but
that's
certainly
yes.
most of the people.
Most people alive today, yes.
I will be disappointed personally if we don't have a strong indication that there's life. And if we don't have one, my conclusion would be maybe it isn't there. Maybe, in fact, there's something special about this solar system.
That would be in violation of the Copernican principle, suggesting that nothing we've ever measured about our circumstances has ever been special.
Either answer to the question is overwhelming.
Right, exactly. That's right.
A new term has developed, astrobiology. Is this, are you comfortable with that term?
Oh, yeah. Astronomers can't do it alone. There's certain questions we know how to ask that don't include the kinds of questions a biologist would ask if you brought him along on a mission. Same is true if you bring along a geologist. Better yet, a paleontologist. If there's some history of life buried within the soils, you need somebody who has experience rummaging through cross-sections of a planet. So there's been a realignment of effort by multiple disciplines, all asking the same question. The chemists, the biologists, the astronomers, we all want to know about life elsewhere in the cosmos. And astrobiology is a nice umbrella term for that, although keep in mind that it's an entire field with no data. Right now, we have not one example of life off of Earth, so they're anxiously awaiting their first sample for the lab.
Well, I won't say it's no data in the sense. I think all this life in extreme environments is, I think...
that's not astro. That's geobiology.
Okay,
Which
I
is
wasn't...
a distinguished, wonderful field.
It's starter data.
Yeah,
It's starter
that's fair.
data.
Yeah,
That's fair.
So, I mean, what's
Practice
really...
data. Practice data.
What's really missing here, actually, is while many fields actually have a theoretical basis, astronomy has a theoretical basis. Certainly physics, which is the granddaddy of all, has a very sound theoretical basis. It took a long time for the chemists to get a theoretical basis with their bonds. The problem is that biology has there is no such thing, at least to my knowledge, of a theory of biology. It seemed very complicated.
What you're almost saying is that you can't make a theoretical biology unless you have more than one data point.
Unless you have more than one data
That's
point.
historically always been the case, right? I mean, chemistry wasn't understood as a
perfectly said.
discipline until you could see patterns and so on. You've got to see patterns, you've got to classify data. You need to do all that butterfly collecting first. And unfortunately, that's why I said, so this is a little difficult subject because you can't do this collection in the field because the field is a bit far away.
It's exciting because this is a unifying human quest.
Yep.
And all peoples, all societies, all groups have the same
For all
meaning
time.
to it.
Yeah.
For all
For all
time.
time.
For all
Yeah.
time. That's a good point.
And call it a quest, not a field. Because it's not a field yet. 'Cause you can't have a field without a single example of life elsewhere. So it's a quest. It is a noble... It's
As
probably-
alchemy was a quest. I mean, people
and
rag
it
on
didn't
alchemy a
pan
lot.
out.
No, but people rag on alchemy. But wait, people rag on alchemy, but consider that at least it was an experimental subject, and it happened in laboratories, and there were important foundations from alchemy that led to chemistry. And so you had to begin somewhere. Alchemy had no theoretical foundation that was working for them.
But
so
it had a wonderfully compelling idea. I could
quest.
take lead into gold.
it had a quest.
That,
Right.
and
With an
that is
interesting
wrong. It's not a